this video, we briefly review the processes of cardiac depolarization and repolarization. We will focus only on those points most relevant to understanding the ECG readout. We will work mainly with the 2D schematic of the heart shown here. The schematic shows the right and left atria, the right and left ventricles, and the specialized cardiac conducting system seen here in grey. You will remember from anatomy that the main components of the conducting system are the sinoatrial or SA node, situated near the entry of the superior vena cava into the right atrium, and the atrioventricular or AV node leading into the bundle of His, which then divides into the right and left bundle branches in the interventricular septum. During each cardiac cycle, the atria contract in diastole to fill the ventricles, which then contract during systole to supply blood to the lungs and the systemic circulation. Contraction of the atria and ventricles is tightly coordinated by a wave of depolarization spreading through the muscular walls of these chambers. The depolarization wave, seen here in blue, reflects movement of charge across myocyte membranes and is in effect an electrical current spreading through the heart. Following systole, cardiac muscle returns to a resting state, and this is associated with reversal of the movement of charge across the myocyte membranes. This second wave of electrical activity, seen here in red, is termed cardiac repolarization. The leads of the ECG machine are designed to detect and record these two waves of cardiac electrical activity. The depolarization wave spreads through the heart in a highly predictable pattern, and to understand the ECG readout, the pattern of spread of cardiac depolarization needs to be understood. Cardiac depolarization is triggered by an electrical pulse generated in the sinoatrial node. This electrical pulse then spreads through the atria, triggering their contraction late in diastole. The atria and ventricles, however, are separated by a non-conducting fibrous septum. The depolarization wave cannot penetrate this barrier, and in order to activate ventricular contraction, the wave must be transmitted into the ventricles by the specialized cardiac conducting system. In a normal heart, the only route by which the depolarizing wave can enter the ventricular conducting system is through the AV node. In order to allow the ventricles to fill with blood following atrial contraction, the AV node initially delays the spread of the depolarization wave. And after this short delay, the depolarizing signal is transmitted into the ventricles via the bundle of His. The bundle of His lies in the interventricular septum and divides into right and left bundle branches. The right and left bundle branches transmit the depolarizing signal into the muscle mass of the right and left ventricles respectively. We should note at this point that the interventricular septum is the first part of the ventricular muscle mass to depolarize, and it does so by movement of current across the septum from the left towards the right bundle branch. We'll see later that this early left to right movement of current in the septum is crucial to understanding several important ECG abnormalities. As septal depolarization is taking place, the depolarizing wave begins to spread rapidly through the bulk of the left and right ventricles. As you can see here, in the walls of the ventricles, depolarization spreads from the terminal fibers of the conducting system outwards from the endocardium towards the epicardial surface of the heart, and also back along the ventricular wall to the atrioventricular groove. The final piece of muscle to depolarize is the upper part of the interventricular septum, and again this occurs by movement of current from left to right. Cardiac repolarization is not truly propagated between cells. However, cardiac myocytes repolarize at different rates depending on their anatomical location within the heart. Within the ventricular wall, there is a gradient in the rate of cellular repolarization. Cells in the epicardial region have the fastest rate of repolarization and repolarize first following ventricular contraction. The rate of cellular repolarization is then progressively slower as we move from the epicardium towards the endocardium. Therefore, perhaps counterintuitively, repolarization spreads through the ventricles in the opposite direction to the depolarization wave. As illustrated here, repolarization begins in the epicardium and then spreads backwards from the epicardial to the endocardial surface of the ventricles. We'll see later that this retrograde spread of ventricular repolarization is important in understanding the normal ECG readout. We will now go on in video 2 to show you how the depolarization and repolarization waves are analysed to produce the normal ECG readout.